Hi, everybody. New topic. The topic here is solids of revolution. And just to give us a little bit of intuition about what we're going to be dealing with, this is the top view of a revolving door, or at least it's supposed to be anyway. Consider the top view of a revolving door. Consider the top view of a revolving door. That's this thing. We're looking at a revolving door from above. The path defined by one panel of the door as it revolves about its axis is a cylinder. So let's just look at one panel of this revolving door. The path defined by this one panel of the revolving door as it revolves about its axis is a cylinder, which I guess is why the housing of a revolving door is a hollow cylinder. So if we take this door panel, this door, and revolve it one complete revolution about its axis, the path swept out by this door is a solid cylinder that has the height of this door panel, and it has the radius, which is the distance from the axis to the end of the door. Now let's look at another case. Similarly, consider a rectangle standing on the x-axis. Now, suppose we revolve the rectangle about an axis that coincides with one of the sides of the rectangle. Here's an axis, a vertical axis, that coincides with the left side of the rectangle. And suppose we revolve the rectangle about this axis. Then the path that is swept by the rectangle is a cylinder. Now let's just see how that happens. We're going to take this rectangle and revolve it all the way around this vertical axis. And here's what we're going to get. We're going to get a cylinder. Whoopee. This actually is significant. And just recognizing what we get when we revolve a rectangle about an axis is going to be the basis for what we're going to be doing for about the next 2 or 3 classes. So make sure that this makes sense, and we'll go on to our next observation. The first question that we're going to have to answer about this cylinder is, what is the volume of this cylinder? Now, I haven't given any dimensions yet. I haven't talked about what the radius is or what the height is yet. But if we take a rectangle and revolve it about an axis and generate a cylinder, we're going to want to know, what is the volume of this cylinder? So that's our first big question that we have to answer. Just to give us some insight on how to compute the volume of a cylinder, uh, let's consider a column with a rectangular cross section. The cross section has length L, width W, and the column has height H. Now, what's the volume of that column? Well, you look at it and you say, this thing, that's nothing more than a box that's been stretched out vertically. The volume is going to be the length times the width times the height. And we're exactly right. That's how we compute the volume of a box. Now let's analyze exactly what it is that we've got here. Notice that as we move from the bottom of the column to the top of the column, the shape of the cross section doesn't change. The shape, the size of the cross section doesn't change. For example, if we look right here, what's this distance? Why, it's L, isn't it? And this distance right here, well, this is W, the width. This rectangular column has a constant cross section from top to bottom. If we cut parallel to the ground anywhere from bottom to top, we get a rectangle that's the same size and shape and area as the bottom. So we can analyze this volume another way also, because we can look at the length times the width. And what is that? That's just the area. It's the area of the base. But length times width is also the area of the rectangular cross section from bottom to top. So we can say that the volume is equal to area of the cross section times the height. And that's going to be an important observation. Now let's consider a column with circular cross section. If we cut across parallel to the ground, the cross section is a circle. So we have a column with circular cross section of radius r and height h. Here's the $64,000 question. What is the volume of the column? Well, wait a minute. We just did this for a column that had a rectangular cross section. And essentially we reformulated it so that it really didn't have anything to do with the shape of the cross section. When we had a column with a cross section of rectangular shape. We said that the volume was the area of the cross section times the height. Now, the fact that the cross section is a circle here shouldn't really change anything, right? So it should be area of the circular cross section times the height. Well, what's the area of this circle? Has radius r? That's all we need to know. Pi r squared, there's the area of the cross section, times the height. So the volume of this column for cylinder is area of the circular cross section times the height. Now this we're going to build on. Okay, next question. What do we get if we revolve a rectangle of height r and width delta x about the x-axis? Here's our rectangle. It has height r. It has width delta x. And we're going to take that rectangle and we're going to revolve it all the way around the x-axis, 360 degrees. What are we going to get? Well, we'll just see. Oh my goodness. Here's our rectangle. And we're going to revolve it about the x-axis. And we get a flat disc. What's the thickness of this disc? Right here. What's that thickness? Well, that's the thickness of the rectangle that generated it, right? The thickness is going to be delta x. And what about the radius of this disc? Well, that's the height of the rectangle, isn't it? So we get a flat disc Now the thickness sort of corresponds to the height of our circular column. See, if we took this disk and laid it on its side, it would be a cylinder, but it would be a very short cylinder, and it would have height delta x. Now the volume of the disk it's going to be the area of the circular cross-section times the height. Let's see, the circular cross-section, that's going to be pi r squared. And the height, in this case, is going to be, let's see, height or thickness. The thickness or the height is going to be delta x. Okay. So let's beat that to death. Okay, just for repetition, what do we get if we revolve a rectangle of height r and width delta x about the x-axis? We get this thing, a flat disk of radius r and thickness or height delta x. And the volume is going to be the same as the volume of a column. The area of the circular cross-section, pi r squared, times the height or the thickness, delta x. I guess from now on we're going to say the volume will be the area of the circular cross-section times delta x or times delta y, whichever one it is. Now, why do we want to do all of this? Okay, I'll finally tell you. Okay, where on earth are we going with this? Here's what we're up to. We're going to take a bounded region in the xy plane and revolve it about a line in the xy plane. For example, here we have a rectangle. It's a bounded region in the xy plane. And let me draw this a lot bigger. Let me exaggerate. Yeah, we're going to revolve it about the x-axis in this case. And we're going, by doing this, we're going to generate a solid object, which we call a solid of revolution. Now let's see exactly what this solid object will look like. We're taking this thing and revolving it all the way around the x-axis. And in this case, what we get is a cone. And let's see. I guess that's all we need to know for now. That we take this triangle, revolve it about the x-axis, and the path that it defines is that of a cone. And the height of the cone is going to be this distance from 0 to 4. So the height will be 4. And the radius is this distance, which is y equals 0 to y equals 1. height. Okay. We just generated a solid of revolution. I need to define a few more things. The line about which the region is revolved is called the axis of revolution. Let's see, anything else that I should define here? I think so. I guess just one other thing. The solid of revolution, in this case the cone, is said to be generated by the region in the plane. So this cone is generated by the region bounded by the lines of the triangle in the plane. Or this cone is generated by revolving the triangle about the axis of revolution. Okay, here's what we're about to do. Here's our goal. Given a solid of revolution generated by a region in the plane, compute the volume of the solid of revolution. And that solid of revolution could be a cylinder, it could be a cone, it could be something shaped like a bullet, could be something shaped like a donut, etc., etc. Whatever regions we revolve around the axis of revolution and whatever solids we get, we want to compute the volumes of those solids. And our procedure is pretty much the same as in an area problem, except instead of adding up the areas of rectangles with delta x, we're going to be adding up the volumes of disks of thickness delta x or delta y. So as is the case with an area problem, with a volume problem, we graph the bounded region, including the points of intersection. Inside the bounded region, we inscribe a typical rectangle of width delta x or delta y. And we do it in such a way that the rectangle is perpendicular to the axis of revolution. So remember when we were revolving about the x-axis? The rectangle was standing straight up and down, perpendicular to the x-axis. Our rectangles are going to be sketched perpendicular to the axis of revolution. Next step, we're going to partition the interval spanned by the rectangles into subintervals of width delta x. And we revolve the ith rectangle about the axis of revolution and compute the volume of that ith disk. So we take the ith rectangle and revolve it about the axis of revolution, and that generates a disk. We compute its volume. 5, we approximate the volume of the volatile. We approximate the volume of the solid of revolution by adding the volumes of the disks. And then finally, to get the exact answer, we let delta x go to 0, or delta y go to 0. And let's just sketch a picture of what these steps are telling us to do. Let's look at this visually now that we have an outline. Let's refer back to the example where we have a triangle sitting right on the x-axis, and we revolve it about the x-axis. What did we get when we revolved this triangle about the x-axis? Didn't we get a cone? This is the solid of revolution that we got when we revolved a triangle about the x-axis. Now, let's see what happens if we follow our algorithm and partition the interval into subintervals of width delta x, and we revolve each rectangle about the x-axis to generate a disk. Let's see. Partition, partition, partition. And here's our first rectangle of width delta x. Here's our second. And here's our third, our fourth, fifth rectangle, and so on and so forth. We're going to generate each of these rectangles about the x-axis. Okay. So we got that first rectangle, and then we got the second one, and then we got the third one, and then we got the fourth one, and the fifth one, and the sixth one, etc., etc. Okay, we revolve this first rectangle about the x-axis, and we get a little bitty cylinder. We revolve the second one about the x-axis. We get a larger cylinder. And then we revolve the third rectangle about the x-axis and get an even bigger cylinder. Oh, look at these. We get all of these concentric cylinders. And what we get when we put all of these cylinders together, or all of these disks together, we get a solid of revolution that is approximately the same shape and the same volume as the solid of revolution whose volume we want to compute. Now, does this thing have exactly the same shape and the same volume as that cone? No. But we're not done yet, because we're going to let the thickness of these disks or little cylinders, we're going to let the thickness of these disks go to 0. And that means we're going to have a lot more of these things. But it also means that as we let delta x go to 0, this shape is going to much better approximate the shape and volume of the cone. So we revolve each of these rectangles about the axis of revolution to generate disks. We stack the disks side by side. And when we do, these disks have, or they form a solid that is approximately the same volume and the same shape as the solid of revolution that was generated by revolving this triangle about the axis of revolution. And the smaller delta x is, the better the approximation is. If we let delta x go to 0, we get exactly the volume of the solid of revolution. Let's do some examples. Here's a nice exercise. Consider the region bounded by the graphs of y equal x squared plus 1, y equals 0, x equal negative 1, and x equal positive 1. Compute the volume of the solid generated by revolving the bounded region about the x-axis. Okay, we're doing a volume of solid of revolution exercise. And the first thing is graph the bounded region. Now, the only thing that we have to think about at all really is this thing. Y equals x squared plus 1. Y equals x squared. It's a parabola that sits on the x-axis, goes through the point 0, 0. To get y equals x squared plus 1, we take the y coordinate of every point on this graph, which is x squared, and we add 1 to it. So to get the graph of this function, we add 1 to the y coordinate of every point on this graph. And what that does is it takes this graph and just raises it up 1 unit. Okay? So now we know what y equals x squared plus 1 looks like. And I will graph the region in earnest. Here's 0, 1. And x equal 1, that's a vertical line going through the point 1 on the x-axis. X equal negative 1, that's a vertical line going through the point negative 1 on the x-axis. Y equals x squared plus 1, that's the parabola. Let me do it like this. Okay. Let's see, when x is 1, y is x squared plus 1 or 2. When x is negative 1, y is x squared, which is negative 1 squared plus 1, 2. Okay, let's see. The only thing we really haven't graphed yet is this. Y equals 0, and that's just another name for the x-axis. So we're taking this region and we're revolving it about the x-axis. Okay? Time for me to pause so I can catch my breath and think. I'm kind of curious as to what this is going to look like. I'm thinking if I revolve this about the x-axis, looks like I'm going to get something like a wheel that I'd mount an automobile tire on. That's what it sort of looks like to me. Anyway, I've done the first part of this. I guess now I just need to move on to step 2, right? Okay, step 2. Inscribe a typical rectangle perpendicular to the axis of revolutions. And remember, the x-axis in this case is our axis of revolution. So this is perpendicular to the axis of revolution. This is x of I on the x-axis, y is 0. This point has x coordinate x of I. What's the y coordinate of this point? Well, this point is on the graph whose y coordinate is given by the x coordinate squared plus 1. So the y coordinate here is the x coordinate squared, x of I squared, plus 1. Ah, looking good. Now, we're only going to draw one rectangle, but we realize that this entire bounded region is going to be filled with rectangles. And the rectangles are going to go from negative 1 all the way to positive 1. So I think we've just done our third step, which is 3. Partition the interval spanned by the rectangle. Spanned by the rectangles, plural. Okay? And each of these subintervals has width delta x. Good. We're good up to step 3. Next step, compute the volume of the ith disk. Here's our ith disk. And we're going to revolve this thing about the x-axis. And the volume of the ith disk is the radius squared of pi radius squared times the thickness, delta x. Just what is our radius? Our radius is this distance right here. And it's just a vertical distance. It goes from 0 on the x-axis to exaby squared plus 1. It's just a vertical distance. So the distance is the greater y coordinate, exaby squared plus 1, minus the lesser y coordinate, which is 0. Okay. So the volume is pi r sub I squared, and r sub I is exaby squared plus 1 minus 0, or just exaby squared plus 1. It's r sub I squared times the thickness, which is delta x. And what do we get here? Pi times exaby to the 4th plus 2 exaby squared plus 1 delta x. Okay. There's the volume of my ith disk. Now, in reality, we're going to take each of these rectangles and revolve them about the x-axis and get disks from here to here. We're going to add up the volumes of all of those disks. That's what we'll do in our next step. Next step, approximate the volume of the solid of revolution by adding the volumes of the disks. This is the volume of the ith disk. The total volume is equal to the sum of the volumes of the disks. So this is approximately the volume of the solid of revolution. It's only one thing we need to do now. Let delta x go to 0. And we get exactly the volume. And we're letting delta x go to 0. We're computing the limit of a Riemann sum as delta x goes to 0. So the summation sign magically turns into an integral sign. And the exaby's magically turn into x's. Delta x magically turns into dx. And the limits of our integral, this is very important, the limits of our integral are the endpoints of the interval that we partitioned into subintervals. That's why I didn't erase this picture earlier. We're going to need to refer back to this when we let delta x go to 0. The limits of the integral are always, always, always the endpoints of the interval that we partitioned into subintervals. Okay, now we can turn the crank and out pops the answer. I hope. We'll get pi fifth over 5 plus 2x cubed over 3 plus x evaluated from -1 to 1. And that's going to equal what? And plug in -1. And let's see, each of these terms is the negative of these terms. And you know what? I don't need that 3 there. But each of these terms is the negative of the corresponding terms here, but there's a negative sign out in front, which means that instead of subtracting, we're going to add essentially the same amount that we already have here. So we're going to get pi is, let's see, a fifth plus a third. Okay, so 3/15 plus 10/15 is 18/15 plus 15/15 is 33/15. Is that right? 3/15 plus 10/15 plus 15/15. 28/15. Double it, 56. 15. I did this for the first time back in 1982. Let's see if I get the same answer. Oh, thank goodness I do. Okay. So the volume is 56 pi over 15 cubic units. And the purpose of these exercises is for us to learn integration. Are we ever going to be asked to solve or find the volume of a solid revolution? Maybe, but maybe not. The real benefit to these exercises is that if we're taking physics, sometimes we have to create our own formulas that turn out to be integrals, and we do it the way we did it here. So there are applications for this, and the application is when there's no formula for what we want, we chop up the space into tiny subintervals, and we inscribe a rectangle and either add up the areas of the rectangles or the volumes of the disks or whatever, and let delta x go to 0, and we've got the integral that gives us the answer. You know what? I think I'm going to call it quits here, and we'll do the next exercise either in class or in the next video. Enjoy it.